In this video, we'll be talking about the actual diode model that we're going to be using for solving circuits by hand. So we have two versions of this diode picture we've talked about. We have the ideal version where the behavior looks like this on our I versus V graph. So it's like 0 current over here and 0 volts over here. We also have this more realistic version that uses an exponential, and this is the closest to what diodes actually do, but incorporating this into our solving equations by hand is kind of tricky. So we have a happy medium that reproduces most of the important features of diodes, but still doesn't give us the problems that this super simple perfect model does. And in terms of these pictures, that model looks like this. It is still 0 out here, but instead of going up to infinite current at 0 volts, it goes up to some positive voltage, this forward bias voltage, and then goes up. And that's supposed to be perfectly vertical. So the value of where this voltage happens, this is the voltage axis, this is the current axis, the value of where this voltage happens depends on what kind of voltage we're using, right? So we talked about this forward bias turn on voltage in the exponential model that was like 0.7 volts for silicon and 0.3 volts for germanium, and that's exactly what this voltage is going to be. So this is our sweet spot model of the diode we're going to be using, and let's go from there. Oh, I guess a couple other things. So our real behavior also has this reverse breakdown that happens. So when we get to some negative voltage, that the current is allowed to flow again. We're not going to worry about that in all of our circuits. We're assuming we're far enough away from that our diodes are not going to conduct current in the reverse direction. And just to be explicit, out here the current is 0. We're not saying the current is minus 100 nanoamps. We're just saying the current is 0. That's close enough. Nanoamps aren't gonna change what's going on here. And I already said this slope was infinite. This is straight up. Okay, so the features of this make this relatively easy to incorporate into solving circuits the way we have been solving circuits. So let's now move also to our diode symbol and how we're going to use it on our circuit diagrams. So our diode symbol looks like this. Sometimes this triangle is filled in, sometimes it's hollow, it doesn't matter. There are lots of modified diode symbols with different modifications of these of this part. So, these all mean different things. So for regular diode, this should just be a straight line. We'll learn about some of the other ones later on in the course. And so on our diode, this side is the anode and this side is the cathode. And what does that mean? That tells us that this circuit symbol is asymmetric, right? Just like the behavior of a diode. And this looks like a arrow, this at least kind of looks like an arrow pointing to the right? And that is because this is the forward bias current direction. This is the direction that current can flow in easily. And if current tries to flow in this direction through the diode, it is stopped, because it hits this straight line. Okay, so let's go to our diode model graph. So that, our diode model looks something like this. So if we need to figure out which direction here is which direction in voltage, right? If this end is higher than this end, is that being over here or is that being over here? Okay, well, we said if current flows this way, that is the easy direction. So that means if this is plus and this is minus, this is the direction that current's going to want to flow, and that is the direction that current is allowed to flow. So this, if we're conducting current, we're maybe somewhere like there, so we're at this positive voltage. Okay, so in other words, on this graph, this situation corresponds to V greater than 0. This is the forward bias where we are allowed to have current flowing. If this end is negative and this end is positive, this is the reverse bias. V is less than 0, and we're at some point over there. And I don't have a current arrow because I is equal to 0 in that case. Okay, so if we have a circuit in a diagram, sometimes you can just look at it and tell if it's going to be forward biased or reverse biased. We'll talk about that in a little bit. But one way we can deal with diodes in our diagram is actually by replacing them with things that we already know how to deal with. So, in other words, if our diode is reverse biased, so if we're at some point out here where this end is at a higher potential than this end, we can replace our diode. I mean, our diode is not going to have any current flowing through it, which means we can replace our diode with just a gap between two wires. So our diode voltage, let's call this V sub D. And so I guess I should try the diode again. So our diode looks like this. So if this end is positive and this end is negative, this is VD greater than 0. This end is negative and this end is positive. This is VD less than 0. Okay, so if VD is less than 0, that is reverse biased. We know we're going to have no current flowing, and we can replace our diode with an open circuit, meaning that we can replace our diode symbol with just a gap between two wires, and we're not going to have any current flowing, and that might make our circuit analysis a lot easier. In fact, this is not just true if this is less than 0, because we can go to 0 and even above 0, and we still have 0 current. So in fact, this is true for any voltage below whatever our turn-on voltage is. For a silicon diode, we're going to assume, for a silicon diode, which is what we're going to assume here, it would be anything below 0.7 volts. All right, so the only other alternative is that we calculate some diode voltage greater than or equal to 0.7 volts, meaning we're on the right half of this. But of course, we can't be at any voltage higher than 0.7, right? There is no solution to this equation for points out here. The highest the voltage can be is 0.7 volts. So really this is like, if we want to try to apply a voltage of greater than or equal to 0.7 volts, it's not going to get there, and we replace the diode with a 0.7 volt voltage source in our schematic. So in other words, our diode that looks like this, we are going to replace with a voltage source that looks like this, where here we're going from left to right, we're going from the high voltage side to the lower voltage side. So that is a 0.7 volt drop going to the right, and that's the same as the 0.7 volt drop going in the forward direction of our diode. Plus minus. All right. Great. So this is actually enough to start solving things in circuits. And these are the only two things we can run into for this simple diode model. So we're going to solve a diode circuit. I guess I should say, because there are these two possibilities, the diode can be on or off. These are kind of our slang for this, I guess. When we have a diode in a circuit, one of the first things to do is to determine if the diode is on or off, and that tells us how to proceed. So let's do a couple real simple diode circuit examples to see what's going on. While I'm erasing, remember that if you're not told anything about a diode in a circuit, you should assume that it is a silicon diode and that turn-on voltage would be 0.7 volts. If I wanted you to do something with a germanium diode where it's a lower voltage, I would tell you that. Okay, so let's say we have a circuit that looks like this. We have a 5 volt voltage source, and we have a 1 kilo ohm resistor, and we have a diode connected in series with everything like this. Okay, so how do we solve this? Well, we need to determine if the diode is on or off, if the diode is forward biased or reverse biased. And so the first thing you can do is say, okay, well, if the diode were not there, what would the voltage across the diode be? And then use that to inform your decision. The other way you can think about it is kind of the alternative. If the diode, instead of being replaced with an open circuit, replace it with a wire and say, okay, if the diode were replaced with a wire, what direction would the current be flowing? So these are two different ways to think about this. And if the current is flowing in the correct direction, the diode is probably on. If it's flowing in the opposite direction, the diode is off, and actually that current is not flowing. So in other words, well, let's just take this. Okay, so if we think about this in terms of the diode voltage, we're going to remove the diode. We'll call this the voltage method. We're going to remove the diode and say, okay, well, without this diode here, with an open hole in the circuit, what does the voltage look like? So here, the current through our resistor is going to be 0 because the current has nowhere to go, so there's no drop. So we have 5 volts and 0 volts. So that means we have 5 volts, this hypothetical situation, we have 5 volts of voltage across our diode, but that's in the opposite direction, right? So in other words, if we had something that looked like this, we would not be able to have current flowing through our diode, and indeed our diode is off. So in other words, we assume that our diode is off, and then we check to see if that assumption makes sense. And in this case, yes, it does. If the diode is off, it is still reverse biased, and so it's consistent that the diode is off. Let's do it the other direction. Let's look at this current method. So here, we're going to assume the diode is on and replace it with a piece of wire. So we're going to say, okay, well, now we can have as much current flowing through it as we want. So if we have a circuit that looks like this, we're going to have current flowing through it like that. So does that make sense for the diode to be on and have current flowing through it in this direction? No, it does not, right? Because this is in the reverse direction. We're not allowed to have current flowing through it. So it is not consistent with these facts that the diode is on. Okay, so in other words, if we assume that the diode is off, we get something that makes sense. We get something that's consistent with the diode being off. If we assume the diode is on, we get something that is inconsistent with the diode being on. We said, okay, assume the diode is on, and we got something that cannot be true if the diode is on. So in other words, from these we can conclude that the diode is in fact off, and we could write diode off or diode reverse biased or something next to it to remind ourselves that when we solve the circuit, we should use that. So in this case, we're going to end up with exactly what we had drawn a moment ago. So that is, we have no current through the resistor. This point is 0.5 volts because there's no drop across the resistor. This side is 0 volts, and we have a pretty boring circuit. No current is flowing because it's trying to go through the diode in the backwards direction. Okay, different circuit. So let's draw, so this is a new circuit. This is unrelated to our last analysis, but all we're doing is flipping the direction of the diode. So here's a new circuit to analyze, and now let's think about each of these two techniques. And let's do them in the same order. So if the diode is off, if we assume the diode is off and replace it with a hole in the circuit, we still have 0 current flowing. We still have this at 0.5 volts and this at 0 volts, but that doesn't make sense with our diode, right? We're not allowed to have 0.5 volts over here and 0 volts over here because our diode can only have a drop of up to 0.7 volts across it in this forward direction, right? If our diode is on, we want to replace it with a 0.7 volt voltage source that looks like this. So this can't be +5 and this be 0. This could be 0.7 and this could be 0, or this could be 5 and 4.3 or something. But this doesn't make sense. So it in that way, it does not make sense for our diode to be off. And let's check the other alternative thing we can check, the current method. So here we assume the diode is on, replace it with a wire, and say, okay, well, we have current flowing through it this way then, right? Current going through our resistor back to there. And does that make sense then with our diode picture? And indeed it does. We're allowed to have current flowing down through this diode, right? That is the forward bias, easy conduction direction. So in this case, our diode is on. So our check here has gone to tell us that this diode is on. So now we have to still solve the circuit. So we have to replace this diode, or one thing we can do at this point is to replace this diode with a 0.7 volt source. You also can kind of look at this and remember that there's, you don't have to actually redraw it. You can just remember that this is going to be delta V equals 0.7 or something like that. But we'll do the full redraw the circuit version. So here, 5 volts across here and 0.7 volts across here. If we're calling this 0 volts down here, that means this point is +5 volts, this point is plus 0.7 volts, and that gives us a voltage difference across the resistor, V sub R, of 4.3 volts. So then the current is equal to V over R, which is 4.3 over 1K, which is going to be 4.3 milliamps, and that is, that is the only missing variable about this circuit. So we don't have to redraw this. We actually, looking at this, if we know the diode is on, we can just right away say, oh, okay, well, if this bottom voltage is 0, this, and the diode is on, it has to drop 0.7 volts going from here to here. So this has to be plus 0.7 volts, and you can just, label that on your diagram and solve the rest of it with that information. All right, so in future lectures, we're going to get into much more complicated diode circuits, but this, at its very simplest, hopefully makes sense, and this is a good start for approaching diode circuit problems.